next we will discuss with event driven simulation techniques. So, event means that when some switching of signals occur, like when a particular signal value changes from 0 to 1 or 1 to 0. So, then that is an event. Actually, since it is a combinational circuit, so as long as input does not change, so there is no requirement of simulating the circuit again, because the output will remain unaltered. So, simulation is necessary only when there is some event. So, if we can identify the events and based on the events we do the simulation, then the amount of simulation that we need to do, so that will be much less. For example, in this particular circuit we see when A, B and C, they were at 0, 0 and 1, output K was evaluated to 1. After that, suppose this A changes from 0 to 1 and B changes from 0 to 1, whereas C remains unaltered. So, both A changing and B changing, both of these are two different events, but for the sake of understanding, so let us consider the case that these two values have changed simultaneously, that is A and B transitions have occurred together. So, what will happen after these events have occurred? Now, this gate G2 has to be simulated again. Before that, based on this topological sorting, we can see we have to simulate G1 first. So, G1 will become 1. So, this remains unaltered. As a result, if this remains unaltered, so this inverter's output, so this does not change. So, this part also need not be simulated. So, the parts that needs to be simulated is this gate, because its input has changed from 0 to 1. After we see that the output does not change, we do not need to simulate any gate to which it fans out. So, this gate G3 has got input from E only. So, nothing has to be done, whereas for gate G2 its input has changed, A input has changed. So, as a result we need to do a simulation of G2. So, that changes H from 0 to 1, and then we find that for G4 its input has changed, there is an event. So, accordingly we have to simulate G4. So, this is a small circuit. So, you see that only a few lines need to be they are spared from simulation, but in a large circuit, so there may be a good number of places where the simulation is not necessary. Zero delay event simulation. So, zero delay means the gates are assumed to be of zero delay. So, there is no delay. So, it is basically starting, reading the initial condition, then it is checking whether there is any more test vector. If there is any test vector, then it will read the new input vector, and after that the active primary inputs, they will be determined, and the fan out gates will be the point to which these primary inputs connect to, that they are fan outs. So, they will be put into a queue, and then say number of gates have been put into queue. So, naturally the queue is not empty. So, this check is false. So, it comes to this side. So, evaluates the next gate from the queue, it takes the next gate G from queue and evaluates it. If there is output change, then we have to put the fan outs of G into the queue again, because those gates again need to be simulated. Otherwise, it goes back and check whether there is any more gate in the queue or not. When this queue becomes empty, then that means for this current test vector we have completed the simulation. Then it has to go for the next test vector. So, in this way it continues. So, as long as there are vectors available in the stimulus file, so it will go on doing the simulation. Once there is no more vector, so the simulation will end. So, that is the zero delay event driven simulation policy. Then this much we had had in the previous class, we have seen some of this. Now, next we will consider the case where there is some delay associated with the gates. Okay. So, nominal delay event driven simulation, that means every gate it will be assumed to have some fixed amount of delay, and this delay is called the nominal delay. So, event driven simulation based on this nominal delay. Now, it is not that as soon as a gate's input changes, gate has to be simulated and output will come immediately, but that will not happen, because now the gate has got a finite delay. So, even if its inputs have changed, it will take some finite amount of time for the output to change. So, what happens is that we can think of a list of timestamps like T0, T1, Ti, that goes in an increasing order. Now, at T0, suppose the line signal line P has to be evaluated, and the new value is Vp plus. So, there is a new value of P in future. So, at time T0, so this evaluation will take place, at time t1. So, we have got 3 changes q, r and s. So, these are the 3 changes to occur. So, their signal values will change to Vq plus Vr plus and Vs plus that way. So, you see that there is a definite delay associated with the gate. So, not only which gates. So, this is the point, that it is not that we have to identify only the gates that we need to simulate, but also we need to identify the time at which the simulation has to be carried out. So, this is basically a 2-pass event driven simulator that takes care of this timestamp as well. So, we start, then there is a check what is the next timestamp. So, if there are some more timestamp, means if there are some events to occur in future, that is scheduled to occur in future. So, then this next timestamp will have some value. If it is yes, then it will get the next timestamp t. So, in the previous list we have seen that these t0, t1, ti. So, these timestamps are there. So, as long as that list is not empty, so it will try to get the next timestamp. If it gets the next timestamp, so it gets the next timestamp t. So, it retrieves current event list LE. So, LE is the event list. So, in this particular diagram, so this is an event list. Similarly, this is one event list. So, this has got a number of events associated with it that are supposed to occur at time t0 or time t1, etc. Now, it comes to this point, if there is no event to occur at timestamp t. Naturally, initially there will be a number of events, but as we are processing the events, then number of events in that list will reduce. So, this is we check whether this event list is empty or not. If it is not empty, then we get the next event g Vg plus from LE. So, for get g, what is the next value that should come. So, we get this thing in LE. Now, there is a check. Actually, what happens is that maybe I have got this gate. So, previously this gate was holding the value, this is the gate Vg. So, this was holding the value Vg. Now, suppose this input changes from 1 to 0. Okay. So, previously both were 1. So, output was Vg was equal to 1. Now, this input changes from 1 to 0. Then depending upon the delay of this gate, say this delay is say 2 millisecond or so. So, if I have started at time 0, at time 2, so we have got this event to be simulated, the gate G has to be simulated, and this new value that will come is this, it has gone from 1 to 0. So, this should become 0. Now, we have to check whether this 0 that is mentioned here is different from the previous value of this gate. So, these two values will be compared. So, that is what is done here. So, we check whether this Vg plus, that is the new value of Vg, is different from the old value of Vg or not. So, if it is not different, if they are same, if Vg plus and Vg are same, then naturally nothing has to be done from the fan out of this gate, because this part will not, the successive fan out parts, they will not change. So, nothing has to be done. However, if these are not same, that means this output has also changed. So, so now we have to think about the fan out gates of this gate G. So, we append G's fan out gates to the activity list LA. So, this is the activity list that is created LA. So, these are list of activities, like what to do, like in this particular case you see that if this gate fans out to say 3 different places feeding 3 different gates, then all these at its destination, maybe it is feeding one AND gate, this is feeding one OR gate, this is feeding an inverter. So, all of them needs to be simulated again. Now, in the activity list we just collect this information that we have to do these activities, we have to simulate these 3 gates in future. So, these activities are added. Now, this then it goes to again this check whether the list of event is empty or not. So, when this list of events have become empty, that means we have got a set of activities to be done. Okay. So, these are we have identified the set of activities to be done, basically the gates to be simulated, they are identified. So, we get the next node next gate G from this activity list LA and evaluate the gate and schedule G Vg plus at time t plus delay of G. So, as I was telling, now this gate has to be simulated. Now, when this simulation will be done, if this delay is 2 millisecond, that means after 2 millisecond time this gate should be simulated, that event should occur after 2 millisecond. So, with this particular activity is added. So, this is this activity is added. So, then after say this is the this new gate. So, this new gate becomes the current G. So, this gate has got a delay of say 1 millisecond, that means after 3 millisecond, at 3 millisecond I have to simulate this new gate. So, this entry has to be added. So, this new gate, let us call it H. So, H and the value of the gate whatever it is based on the other inputs of the gate. So, that will be evaluated and that will be added to the event list at t plus delay of this new gate. So, this way this 2 pass simulation will go on. So, this is called 2 pass because in the first pass we are taking this, we are taking an event and then we are finding out all the future activities. Okay. Then in the next pass for all those future activities, so they will again be updated, they will be put into the list, and then when this activity list becomes empty, that means corresponding to this event we have so corresponding to the current timestamp. So, based on that whatever event list we had, so whatever events are to be simulated, so all of them have been completed, their activities have been identified and all that. So, simulation should advance to the next timestamp. So, when this LA becomes empty, so it is counted here, it is coming back here, so that the next timestamp is taken up and simulation will continue like this. So, this is an example. So, it is assumed that the nominal delays for gates G1, G2, G3, G4 they are 8, 8, 4 and 6 nanoseconds. Okay. Now, at time 0, so we have got this A, B and C, these inputs are assumed to be 1, 0, 0. So, this is the event that A becomes 1, B becomes 0, C becomes 0. Now, since so these are the times. Okay. So, A becomes 1. So, A becomes 1 at time 0 and then we need to the activity corresponding activity is that the G2 has to be simulated. So, the activity becomes G2. Similarly, at time 2 C becomes 0. So, the activity for this is again we have to simulate G1 and B being 0 at time 4. So, again activity is that G1 has to be simulated. Now, based on that, so when this activity is taken up, so based on this activity we find out that what is the current value of line H. So, line H is this is 1. So, this has to be simulated and found that it is 1, but we know that G2's delay is 8, okay, 8 nanosecond. So, that means this scheduling of this particular event will occur at 8 nanosecond. So, this way this list will grow. Okay. So, we find out the activities and then accordingly we find out the events and they are put into this list and simulation proceeds by that. This is the same information put in a timing diagram form. So, when A has occurred, so A makes a transition from 0 to 1 at time 0. So, that triggers this particular event. Okay. So, these are actually all these edges are all events. So, this triggers the event that H will make a transition from 0 to 1 at time 8. Then, so everywhere say C makes a transition from 1 to 0 at time 2, that means this will be triggered, this will trigger at this point, but it may not have any effect. Okay. So, here it does not have any effect, it does not change. So, E remains unaltered, though this simulation has to be done and this has not triggered any new action, whereas when this H changes it has triggered a new action, but since here E did not change. So, E could not trigger any new action. Okay. So, if we just compare side by side this compiled code and this event driven simulation, in case of compiled code it is a cycle based simulation. So, naturally high switching activity circuits will come into picture, because every cycle we are going to simulate the circuit. So, if the circuit has got lot of switching in it, then it is better to go for a cycle based simulation, because if we try to generate the event list, then event list will also be very large. So, it is there is no point maintaining additionally this data structure. So, that will increase the complexity of simulation. So, if we have got high switching activity circuit, so it is better that we do not go for this event driven simulation, rather we do a code based simulation. So, third important thing is that is code based simulation we have seen that it can do parallel simulation. So, multiple multiple stimulus they can be simulated parallelly, because taking help of this word size of the processor. So, that way it can help us in running the simulation faster. However, compilation times are necessary. So, naturally it will be limited by the compilation time. So, we have to give extra time for doing compilation, and anything you change in your circuit design. So, again the code has to be compiled, and particularly if it is if you are doing on a platform which is, if you are doing the simulation on a platform which is different from where you have compiled it. Okay. So, basically the cross compiler sort of things, then naturally we have to again go back to the cross compiler and do the compilation, and again come back to the target machine and do the simulation. So, that way it becomes sometimes cumbersome. On the other hand, if you take event driven simulation, the advantage is that it implements gate delay, and thus it can help in detecting hazards. So, compiled code simulation. So, since it is cycle based simulation, so every time it is changing, so it will just show that information, but whether any hazard is occurring, like there is no delay. Actually this compiled code version was basically a zero delay version. So, we could not get the hazards into picture, whereas in case of event driven simulation, since every transition is taken as an event, so if there is a hazard in the circuit, so that will also get detected, and it is particularly suitable for low switching activity circuits, because low switching activity circuit, if you are going for a cycle based simulation, then every cycle will simulate the circuit, but which is unnecessary, because ultimately the circuit inputs or internal gates, they do not change their state. As a result, it is just wastage of CPU time for simulation, and naturally the memory management will be more complex. So, we have got those linked lists, the event list and activity lists. So, maintaining them becomes a bit cumbersome. So, dynamic memory based policy has to be used, and it has got naturally its own difficulties. So, this is an example of hazard. So, hazard is an unwanted transient pulse or glitch. So, what happens is that you see in this particular case A, B and C, so their values were 1, 1 and 0. So, 1, 1 and 0. So, now suppose this B changes from 1 to 0. So, 1, 1, 0 and B now changes to 0. So, as if it changes to 0, what will happen? So, this will become 1, sorry, this will become 0. As a result, this H will become, so let us see what it was previously. It was A was 1, B was 1 and C was 0. So, 1, 1 and 0. So, it was so this value was 1, this value is also 1. So, H value is 1, and so this NOR gate output was 0. Now, if you, when this B makes a transition from 1 to 0, then what happens? This B goes from 1 to 0. So, as a, but C is at 0. So, this value becomes 0. As a result, this J value becomes 1. So, NOR gate will continue to remain at 1. The K will continue to remain at 0. So, this is the behavior. However, if we consider that the inverter has got a delay of 3 nanosecond and other gates have got delay of 2 nanosecond, what will happen? This inverter, so when this B value changes from 1 to 0. So, this E value change it occurs after 2 nanosecond, because this OR gate G1 has got a delay of 2 nanosecond. So, after 2 nanosecond E value will change to 0, and when E value changes to 0, this inverter has got a delay of 3 units. So, J, it changes its level after 3 time units. So, J becomes 1 at this time. Now, this OR gate, so what happens is this OR gate has got a delay of 2 nanosecond. So, for some time it finds that both the inputs are 0. So, this is H is also 0 and J is also 0. So, it becomes equal to 1. This NOR gate value becomes equal to 1, and when it becomes equal, after some time, of course, this inverter will rise. As a result, this will fall back and it will become 0 again. So, this is a hazard. So, in this circuit that is present. So, if we assume a 0 delay model, then we cannot identify this type of hazards, but if we have got which is quite practical, that gates will have some finite delay. In fact, wires will also have some finite delay. So, if we consider those delays into picture, then of course, these hazards will come. So, if these hazards occur during the circuit operation, then there may be problem, because the value of the signal may be sampled when that hazard has occurred. So, as a result it will get an improper value. And second thing is that this, due to this hazards, there will be unwanted transitions in the circuit. So, that will increase the power consumption of the circuit. So, it is better that at the design stage we resolve these hazards. But first of all, to identify, we have to identify the hazard. So, this way we can identify the hazard. Now, there are mainly two types of hazards, static hazard or dynamic hazard, static or dynamic, where a static hazard is a transient pulse on a signal line whose static value does not change. So, there can be a static 1 hazard or static 0 hazard. So, static 1 hazard means the line was remaining 1, there is a hazard. So, it comes to 0, and then it again after some time it goes back to 1. So, there is a high to low transition. So, there is a small high to low pulse occurring, which is on a signal line which should otherwise be continually high. Similarly, static 0 hazard means the line should ideally be at 0 level, but due to the presence of this hazard, it makes a transition and it goes to 1 for some time in between. Now, this is static hazard because the initial value and the final value of the signal line, they are same. Now, if the situation is like this, that the initial value and the final value of the signal line are not same, in that case it is called a dynamic hazard. So, what has happened in this case? You see, the initial value of the signal line is 0, final value of the signal line is 1, but it should make a, ideally it should make a transition from 0 to 1, but what has happened is it has made a transition from 0 to 1, but instead of being settled there, so it comes back to 0 and then again makes a transition to 1. So, this high, so low to high, then again high to low. So, this particular transition, so this is basically a dynamic 1 hazard, because it is dynamic, it is going to 1, the signal value is going to 1. So, it is called a dynamic 1 hazard. On the other hand, so we have got dynamic 0 hazard also. So, that is the initial value was high and final value is low, and in between it sees this type of transition, the signal line goes down to 0, then it becomes 1, and then again it goes down to 0. Okay. So, this is these are the different types of hazards that we can have. Now, how do we detect these hazards? Okay. So, if we see that suppose V1 and V2, so they are two consecutive input vectors. So, I have got a circuit that has got n inputs, and these V1 and V2, they are two n bit vectors. So, I have this V11, V21, Vn1. So, these are the individual bits of the vector. So, these first we, so if we want to see that if there can be a hazard between these two, so what we do? So, we add a new vector V plus, so which is given by V1 plus V2 plus etc. How is it defined? So, it is defined like this, that Vi plus is equal to Vi1 if Vi1 and Vi2 they are same. So, for example, if V11 and V12 are same, then this will be called they are same. So, we will keep the same value. Otherwise, if these two values are differing, okay, if these two input values are differing, then we say that we do not know the value. So, this is unknown. So, Vi plus is set to unknown. So, in this way we set this particular vector V. Okay. Then we simulate this particular sequence of patterns. Okay. V1 V plus, first V1, then this V plus, this vector that we have created, and then the V2. Now, if so this simulation, since we have got U into picture, so we have to do a ternary simulation. So, once we are doing this ternary simulation, so if we find that any signal value has got this type of thing 1 U1 or 0 U0, that means there is a possibility of a static hazard, because in between the value of the signal is becoming unknown. So, it may be 0, it may be 1. If it is 0 during operation, then there is of course there is the hazard. If it is 1, then there is no problem, but at the time of simulation we do not know whether this value is permanent, is exactly 1 or exactly 0. So, that is why simulator has given you and given it as an U. So, this presence of U in between, so that identifies the hazard, possibility of hazard. So, how do you simulate this multi-valued logic for hazard detection? So, so for the static 0 and static 1, this 6 valued logic is sufficient. So, because static 0, so this static 0 is in a 6 valued logic. So, we have got these 6 symbols: static 0, static 1, rise transition, fall transition, static 0 hazard and static 1 hazard. So, up to this symbol 0, 1, R, F, 0 star and 1 star. So, they are they are the symbols for 6 valued logic. Now, their actual values have been assigned in such a fashion that if we do AND or operations with them, so we will be getting the hazards. Like here, say this if a line is permanently 0, static 0, so that will be coded in a 6 valued logic as 0 0 0, whereas 1 in 6 valued logic, something that is 1 is actually represented by 1 1 1 triple 1. A rise transition is that it is 0 to 1, it is going from 0 to 1, and in between we have said that since in between if you sample, so you may get a 0 or you may get a 1, it depends on the time at which you are sampling the signal. So, that is coded as 0 u 1, because in between we are uncertain about the value of the line. Similarly, a falling transition, so depending upon the point at which you sample the line, so you may at the beginning you will definitely get a 1, at the end you will definitely get a 0, in between you may get a 0 or you may get a 1. So, that is coded as 1 u 0. So, static 0 hazard means you are getting a 0 at the beginning, getting a 0 at the end, but in between you may get a 0 or you may get a 1. So, when you get this 0 u 0, that represent a static u hazard, and this 1 u 1, so that represents a static 1 hazard. So, first one is static 0 hazard and this is static 1 hazard. So, same thing if we extend to 8 valued logic, then it is like this, that 0 is coded as 4 zeros, 1 is coded as 4 ones. A rise transition is represented by tuple like this. So, it can be 0 0 0 1, 0 0 1 1, because there is a rise. So, it is going from 0 to 1. So, you see in all the cases it is the signal line is going from 0 to 1. In between if you sample, you may get a 0, you may get a 0 0, 0 1 or 1 1. So, that way it is coded. So, in this way this these logic values have been assigned to different symbols, so that if you do AND or operations over them, so you will be getting the corresponding symbols. For example, if you are doing say AND of two static 0 and static 1 lines, so you do a bitwise ANDing, so you get all 0, so that is 0. So, 0 and 1 is 1. On the other hand, if you are ANDing with say 0 and this falling transition, this one, so it is basically given by individual bitwise ORing. So, OR of 0 and this rise a falling transition. So, you have to do bitwise ORing of all of them. Naturally, you will get this falling transition itself, okay, because ORing with 0 will give you 0 only. So, all the 3 symbols are to be ORed. So, as a result you will get again this particular tuple containing 3 symbols. So, that means falling transition or static 0. So, that is giving us a falling transition. So, this way all these symbols have been assigned in such a fashion that this AND or NOT rules, they work properly. Next, we will go towards a fault simulation. So, logic simulation is okay. We can when we are doing at logic level, we are evaluating the circuit, etc. But under some existence of faults in the circuit, so we need to know what is the output pattern, and if we get that information, so if that we will check whether it is different from the good one or not, and if it is different from good one, then definitely we have got the fault detected. So, this fault simulation will actually try to give a figure of merit to like how good or bad is a given test set and all that. So, the way we will proceed is like this. We will start with an introduction, then we will see different styles of this fault simulation techniques. Okay. Serial fault simulation, which is the simplest one, then we have parallel fault simulation, deductive fault simulation, concurrent fault simulation, differential fault simulation, fault detection. Then we will also see some comparison between these fault simulation techniques and alternative to fault simulation. Finally, we will see some concluding remarks. Okay. We will continue with this fault simulation in the next class.